Welcome to the Deep Dive. We're plunging headfirst into a field that's, well, not just rapidly evolving, but utterly transforming how we work and live. AI engineering.
It really is.
I mean, if you've been amazed by tools like GitHub Copilot writing complex code, maybe with surprising accuracy, or Mid-Journey conjuring up these stunning images from just a few simple words, you've seen the power of AI in action.
Absolutely. Those tools, driven by what we call foundation models, they're genuinely changing everything. And the demand for people who can build with them, it's skyrocketing.
Yeah, I've seen some of those salaries mentioned AI engineering roles commanding, what, $300,000 or more. It's pretty staggering.
It reflects the demand, definitely.
Yeah.
So today, we're taking a deep dive into this really dynamic field, and we're using a monumental work as our guide. AI Engineering by Chip Huiyan.
Right, and this isn't just any book. It's, what, 800 pages. Really comprehensive guide.
Exactly. Luke Metz, who co-created ChatGPT and used to manage research at OpenAI, he described it as a vital guide to end-to-end AI system design, from model development and evaluation to large-scale deployment and operation. It's truly an indispensable resource for understanding how these real-world AI applications get built.
So our mission today, for you listening, is to act as your expert guides. We're going to try and extract the most important nuggets of knowledge from this incredibly detailed technical book. We want to give you a high-level, yet thorough overview of the field and its core concepts. Think of this deep dive as maybe your shortcut to getting well-informed about how these powerful AI systems are constructed and deployed.
Yeah, we'll unpack everything from the basics of foundation models and prompt engineering through things like Retrieval-Augmented Generation, RAG, you hear that a lot, and fine-tuning, all the way to optimizing how these systems actually run, the inference part.
And we'll explain everything step by step, grounding it in real-life project scenarios, trying to make these complex ideas really tangible and actionable for you.
And it's really crucial to understand this book prioritizes what it calls timeless foundational knowledge. It's not just about the latest tools that might be outdated next year.
That's a good point.
Andrei Lopatenko, director of Search and AI at Neuron 7, he put it perfectly. This book serves as an essential guide for building AI products that can scale. So we've really dug into the insights directly from the book, and you'll hear us referencing important sections by chapter name. We want to make sure you get the most accurate, valuable information straight from the source.
Okay, so let's dive in. Let's get to the core of what AI engineering is all about, starting right at the foundations of these models. We're drawing from the first two chapters of Chip Huiyan's book, beginning with Chapter 1, Introduction to Building AI Applications with Foundation Models. So what's the why now? Why this huge explosion of interest and investment in AI engineering just recently?
Well, it's really what the book calls a perfect storm. You've got AI models that have dramatically improved their ability to solve actual real-world problems. And at the same time, the barrier to building with them has dropped significantly.
Okay. So better tools, easier access.
Exactly. And that convergence has created one of the fastest growing engineering disciplines we've probably ever seen. As Chapter 1 notes, if I could use only one word to describe AI post-2020, it'd be scale. And that scale refers not just to the model size, but also their massive resource consumption.
And the economic impact is undeniable, right? Goldman Sachs estimates AI investment could hit, what, $100 billion in the U.S. and $200 billion globally by 2025. That's huge.
It's a massive surge. And you see it in the market, too. S&P 500 companies that mention AI in earnings calls, their stock prices jumped an average of 4.6%. That tells you how much value and momentum the market perceives. Businesses feel they have to adapt now.
So let's define it clearly. What is AI engineering and how is it different from, say, traditional machine learning?
Okay, so at its core, AI engineering is about building applications on top of these existing foundation models. It's generally not about building those massive models from scratch.
Right. So less focus on training from zero, more on adaptation.
Exactly. In traditional ML, engineers often focused on developing and training models from the ground up for specific tasks. AI engineers, though, they leverage these powerful pre-trained foundation models. Their focus shifts more towards adapting these existing systems to solve specific business problems.
And this model as a service idea has been a big part of that shift, hasn't it? Like using APIs from OpenAI or Google.
A huge part. These companies popularized exposing their models via APIs, so you don't need the massive infrastructure or the deep expertise to host and serve these incredibly complex models yourself anymore.
You just make an API call.
Pretty much. It dramatically lowers the barrier to entry. It's kind of like going from needing to build your own power plant to just plugging into the electrical grid. It makes advanced AI accessible to way more developers and businesses.
So what was the breakthrough that actually enabled these foundation models in the first place? You mentioned self-supervision.
Yes, self-supervision. This was key. It elegantly solved a major bottleneck: data labeling. Traditionally, ML models needed humans to painstakingly label huge data sets. Very expensive, very slow. Self-supervision gets around that. The models learn by predicting parts of their own input data. Chapter 1 gives a simple example. From the sentence, "I love street food," the model can create maybe 6 training samples like "I love street" or "I love food," predicting the masked word each time.
So it generates its own labels, in a sense.
In a way, yes. This allowed for creating vastly larger data sets for models to learn from, enabling them to scale up exponentially. As Chapter 1 states, the answer is that language models can be trained using self-supervision, while many other models require supervision.
And this led to that rapid evolution we saw, from simple language models to LLMs, and now these multimodal models.
Exactly. We went from basic language models to large language models, LLMs, like the early GPTs. But then they expanded further to handle multiple data types images, video becoming large multimodal models, LMMs, like GPT-4V or Claude 3.
So it broke down those old silos like NLP for text, computer vision for images.
Precisely. Now, these foundation models handle diverse data, laying a common foundation, hence the name for all sorts of AI applications. Chapter 1 defines it well. The word foundation signifies both the importance of these models in AI applications and the fact that they can be built upon for different needs.
And the use cases are everywhere now. Coding assistants like Copilot, image generation like Midjourney.
Adobe Firefly, writing aids, customer support bots, sophisticated data analysis systems. It's incredibly diverse.
Let's think about a practical scenario. AI in the workplace, especially for developers. McKinsey's data shows it boosts productivity, right?
Significantly, especially for simpler, repetitive coding tasks. Companies can potentially achieve more with fewer engineers. It's even disrupting outsourcing, as those simpler tasks are prime candidates for AI automation.
Think about a developer using Copilot. They can churn out boilerplate code or debug much faster. That's a direct impact on project timelines, on budgets.
Absolutely. And another big area is education. Instead of banning AI, many schools are now exploring how to use it to help students learn faster.
How so?
Well, AI can summarize dense textbooks, generate personalized lecture plans for individual students, adapt materials to different learning styles. Like an auditory learner could have AI read things aloud, a visual learner could get custom visualizations.
That's a fundamental shift. And we saw the economic impact with Chegg, the homework help company. Their stock plummeted because students started using AI instead.
Yeah, a very direct consequence.
And that study on exposure you mentioned, Elandu et al., 2023, it defined exposure as AI cutting task time by 50%. Who's most exposed?
High exposure roles, where maybe 80% or more of tasks can be sped up by 50%, include interpreters, translators, tax preparers, web designers, writers. On the other end, jobs with almost no exposure include cooks, stonemasons, athletes. It gives you a concrete sense of where AI is making the biggest inroads right now.
Okay, so to actually use these general models for specific things, AI engineering uses 3 core techniques.
That's right. Prompt engineering, Retrieval-Augmented Generation, or RAG, and fine-tuning. And the book really emphasizes that adapting an existing model this way is way easier than building one from scratch.
The difference being?
The book gives an example, maybe 10 examples in 1 weekend versus 1 million examples in 6 months. That efficiency is really the cornerstone of modern AI application development. It makes it accessible.
All right, so we get the why now and the what. Let's peek under the hood now. How are these foundation models actually built? Understanding their origins helps us use them better, right? Chapter 2, the making of a foundation model.
Exactly. As Chapter 2 highlights, Chapter 2 analyzes the making of a foundation model and the design decisions with significant impacts on downstream applications. It covers the training data, architecture, scale, and alignment. Understanding these choices helps you, as an AI engineer, leverage and optimize the model effectively for your specific use case.
Let's start with the training data recipe. Where does all this data come from, and what are the issues?
Most large models are trained on vast amounts of web crawled data. Common crawl is a big one, but that scale comes with problems. Clickbait, misinformation, toxic content, it's just scraped from the web.
So how do they filter it?
They use various techniques. For GPT-2, OpenAI used Reddit links with at least 3 upvotes as a heuristic for somewhat higher quality content. It shows that just having more data isn't enough. Quality and relevance are key.
And the data itself is skewed, particularly in terms of language.
Hugely skewed. About half of crawled data, 45.88%, is English. This leaves languages with millions of speakers like Punjabi, Swahili, Urdu, severely underrepresented.
Which is why specialized models for specific languages are so important for global applications.
Absolutely crucial. And there's domain skew, too. Common Crawl leans heavily towards business, tech news, art. For specialized fields like drug discovery, protein data, or cancer screening, X-ray data, general models might not cut it without adaptation.
Like DeepMind's AlphaFold for protein structures.
Exactly. That was trained specifically on protein data.
And these skews have real-world costs, right? Like non-English models being slower and more expensive because of tokenization.
Yes. Tokenization is breaking text into units the model understands. The book cites the massive data set where, say, Hindi text needs a median of 32 tokens to convey the same meaning as 7 tokens in English. Burmese needs 72.
Wow.
That directly impacts cost and latency for applications in those languages. Language-specific optimization becomes critical.
Okay, let's shift to model architecture. The transformer is dominant, built on the attention mechanism.
Yes, the transformer is king right now. And the attention mechanism was the revolution. Before that, models often processed input sequentially.
Like reading a book one word at a time, hard to remember the beginning.
Exactly. And slow for long sequences. Attention, as the book puts it, is like being able to reference any page in the book while answering questions. It lets the model weigh the importance of different input tokens when generating each output token.
So it can process input tokens in parallel.
Right, which speeds up training and inference significantly. That's also why longer context windows get computationally expensive. More tokens mean more things the model needs to pay attention to. And attention is usually multi-headed. Llama 2.7b has 32 heads, letting it focus on different aspects simultaneously.
And the 2 phases, prefill and decode. Why does that distinction matter for optimization later?
So the prefill phase processes all input tokens in parallel to create an intermediate state. It's generally compute-bound, limited by processing speed, FLOPS. The decode phase generates output tokens one by one. This involves loading large weight matrices repeatedly, making it memory bandwidth bound. Knowing this tells you where to focus optimization efforts, which we'll cover in Chapter 9. It's crucial for efficient applications.
Are there alternatives to transformers emerging?
Yes, innovation continues. State space models, or SSMs, like Mamba and Jamba, show promise. They scale linearly with sequence length, offering memory efficiency advantages for very long contexts. Jamba even mixes transformer and Mamba layers.
Okay, model scale and compute. We hear about billions of parameters. What does that mean practically?
Generally, more parameters mean greater capacity to learn and better performance. Parameter count helps estimate compute needs, though it can be misleading for sparse models with lots of zero-value parameters.
And the scale has grown dramatically. GPT-1 had 117 million parameters. Now 100 billion is considered large.
Right, and it keeps growing. The key takeaway is larger models are powerful but demand significantly more compute, impacting deployment cost and infrastructure.
And it's not just parameters, but training tokens. What's the difference?
Good question. The tokens in the dataset aren't the same as training tokens. Training tokens count the total number the model sees during its entire training run. If a 1 trillion token dataset is used for 2 epochs, passes, that's 2 trillion training tokens.
Which means immense compute costs. The GPT-3 example is mind-blowing, 256 H100s for almost 8 months.
It illustrates the scale. And the book notes that even small improvements in fundamental metrics during training can lead to big differences in the quality of downstream applications. That justifies the huge investment.
So after this massive pre-training, the model isn't quite ready for prime time. It needs aligning to human preference, post-training.
Correct. Pre-trained models have 2 main issues. First, they're optimized for text completion, not conversation. They might just continue your prompt instead of answering it. Second, the web data they're trained on contains biases, misinformation, toxic stuff. Post-training aims to fix both, making them safer and more useful.
How do they start that alignment? Supervised fine-tuning, SFT.
That's the first step. The model is fine-tuned on high-quality, human-curated demonstration data. These are instruction response pairs showing how the model should respond. InstructGPT, for example, is fine-tuned on tasks like summarization and translation using human examples. The quality of the human labelers here is critical.
And the second step is RLHF reinforcement learning from human feedback. This sounds complex.
It is, but it's powerful. It starts with collecting comparison data. Humans rank multiple model responses to a prompt, saying which they prefer. It's cheaper than writing responses from scratch, maybe $3.50 per comparison versus $25 per response.
Okay, humans rank responses,
Yeah.
then what?
That comparison data is used to train a separate reward model, RM. Its job is to predict human preferences, essentially, to score responses like a human would. Then, the original SFT model is trained further using a reinforcement learning algorithm, usually PPO, proximal policy optimization, to maximize the scores given by this reward model. It learns to generate responses humans are likely to prefer.
But some companies skip the RL part and use a best-of-N strategy.
Right. Instead of the complex RL training, they just use the reward model directly. They have the main model generate, say, 5 responses, N5, then use the RM to score them and pick the best one. Chapter 2 notes this leverages how a model samples outputs to improve its performance. It's a pragmatic way to boost quality without full RLHF.
That brings us nicely to sampling. Models are
Right.
probabilistic, right? They don't just give one answer.
Exactly. As Chapter 2 puts it, a model constructs its outputs through a process known as sampling. It calculates probabilities for all possible next tokens. How we choose from those probabilities shapes the output.
Like greedy sampling versus other techniques.
Yeah, greedy sampling always picks the highest probability token, leads to predictable, often dull text. To get creativity, we use sampling techniques controlled by variables.
What are the main variables we can tweak?
3 key ones. Temperature controls confidence creativity. Higher temp, 0.7 to high 1 means more creative. Lower, near 0, means more deterministic. Top K sampling limits choices to the K most likely tokens. Top P sampling selects the smallest set of tokens whose combined probability exceeds a threshold P. This probabilistic nature explains inconsistency and hallucinations.
And how does best-of-N relate to test time compute for quality improvement?
Test time compute is essentially applying the best of N idea during inference. Generate multiple responses, pick the best based on some criteria. Like, if generating SQL, keep generating until you get a valid SQL query.
That Tiffin example is great. Generate multiple complex answers in parallel. Show the user the first one that's valid. Hides latency.
Exactly. It improves user experience by delivering a good answer faster.
Getting structured outputs like JSON is often crucial for integrating AI with other systems. How's that done reliably? Beyond just hoping.
It's a common need, especially for agents. Some frameworks help, and APIs like OpenAI's offer a JSON mode, which guarantees the format, but maybe not the content's validity.
So what's the most reliable way?
Chapter 2 is clear. Fine-tuning a model on examples following your desirable format is the most effective and general approach. It's much more robust than just prompting or post-processing, especially for critical workflows.
Okay, let's face the challenges of this probabilistic nature. Inconsistency and hallucination. Why the inconsistency and how do we mitigate it?
Inconsistency can be jarring. If the same input gives different outputs, Chapter 2 suggests solutions. Caching the answer is simple and effective. Fixing sampling variables, temperature top K, makes output more deterministic. Fixing the seed controls initial randomness. These help, but slight input variations causing big output changes is a deeper issue needing careful prompt design.
And hallucination. Models confidently stating nonsense. We saw the legal case example. Why does this happen and what can we do?
It's a major hurdle. Chapter 2 discusses hypotheses. Maybe it's a side effect of RL, or maybe a mismatch between the model's knowledge and the human labeler's knowledge during SFT. If labelers provide answers based on external knowledge the model lacks, the model learns to, well, make things up.
How do we mitigate it, even if we can't eliminate it?
Several techniques exist. Self-check GPT generates multiple responses and checks consistency. Safe breaks output into facts, uses a search API, and verifies consistency. Textual entailment checks if a statement logically follows from a context. These are vital for trustworthy AI, especially in fields like law or medicine.
Right, that makes sense. Let's shift gears to ensuring our applications actually work well. Evaluation, chapters 3, 4, and 5. Starting with chapter 3, evaluation methodology. Why is evaluating AI systems so much harder than traditional software or even traditional ML?
It really is significantly harder, as Chapter 3 notes. It can even consume the majority of your development effort. Several reasons. The problems are complex and open-ended, like writing a poem, many correct answers. The models are black boxes, you only see outputs. Public benchmarks get saturated quickly, needing constant updates. And frankly, there's often underinvestment in evaluation compared to model building.
And the consequences of getting evaluation wrong can be severe.
Tragically so. The book mentions the chatbot linked to a suicide, lawyers submitting AI hallucinated evidence, Air Canada being liable for its chatbot's misinformation. It underscores why robust evaluation is absolutely critical for responsible AI deployment. It's not an afterthought, it's central.
Before diving into complex application evaluation, let's cover the basics used during training. Cross-entropy and perplexity. What do they tell us?
These are core metrics for language models during training. Cross-entropy measures how well the model predicts the next token. Lower means better prediction. Perplexity, as Chapter 3 defines it, is simply the exponential of cross-entropy. It measures the amount of uncertainty a model has. Lower perplexity means less uncertainty, more confidence. Useful for guiding training, but less reliable for models after SFT or RLHF.
Okay, when can we use exact evaluation or functional correctness?
When there's an unambiguous right answer. Multiple choice questions, coding tasks, gaming bots, the gold standard is functional correctness. Did the system do what it was supposed to do, like booking the correct restaurant reservation? It's often binary, right or wrong.
And the coding example is good here, execution accuracy.
Yes, for coding it means, does the generated code run, and does it produce the expected output for test cases? Like GCD 1520 should return 5. The metric is pass at K. Generate K code samples for a problem. If any of them pass all tests, the problem is solved. Pass at K is the fraction of solved problems. It measures how often tools like Copilot give working solutions.
What about tasks without a single right answer, like summarization? That's reference-based evaluation.
Exactly. Used when you have reference data, human or AI generated, 2 main types. Lexical similarity measures token overlap, BLEU, Roge, Shea, needs good references, and overlap doesn't always mean better meaning. Semantic similarity measures if texts have the same meaning, using embeddings, like cosine similarity. Doesn't strictly need references, but depends heavily on the embedding quality. This extends to multimodal embeddings like CLIP for comparing images and text.
Now, a really interesting and increasingly common method, using AI as a judge, turning AI on itself to evaluate. What are the pros and cons?
It's a powerful paradigm for production evaluation. AI judges are fast, cheap, easy to use. They can work without reference data and judge attributes like correctness, toxicity, hallucination presence. Studies show good correlation with humans. GPT-4 had 85% agreement on MT-Bench. Plus, they can often explain their decisions, adding transparency.
How do you prompt an AI to be a good judge?
You need clarity and consistency. Include the task, the criteria, the scoring system. Few-shot examples, showing good-bad responses with scores, usually work better than zero-shot. And you don't always need your biggest model. Smaller, specialized models can be effective judges, saving cost and latency.
But they have limitations too, like being probabilistic.
Yes, several limitations. They are probabilistic, same input might get different scores. Metrics aren't standardized across systems. And they can have biases. Self-bias, preferring their own model type. Position bias, favoring the first answer. Verbosity bias, preferring longer answers. These need careful handling, like randomizing order, but that adds cost.
And comparative evaluation, where AI picks the best of 2, used for leaderboards. What's the key warning there?
A crucial one from Chapter 3. Preference-based voting shouldn't be used for correctness questions. Asking a user which of 2 math answers they prefer is pointless if they don't know the right answer themselves. Preference voting works for subjective quality, not factual accuracy. Leaderboards like LMSYS Chatbot Arena use this, but it has limits.
Okay, we know how to evaluate. Now, which model to pick? Chapter 4, Model Selection and Data Contamination. Selecting the right model seems like a recurring challenge.
Absolutely. It happens multiple times during development as you try things or new models appear. It's a critical, ongoing decision.
A fundamental choice is open source versus proprietary models. What are the key factors to weigh up there? Seems complex.
It is, and it's unique to each team. Key factors include 1. Data privacy. Strict policies might forbid sending data outside. Remember the Samsung ChatGPT leak? Self-hosting or private cloud APIs are needed then. 2. Control and flexibility. APIs mean dependence on the provider. Self-hosting gives full control but needs serious engineering effort. 3. Cost. APIs charge per use, potentially expensive at scale. Self-hosting has high upfront and ongoing engineering costs. It's a classic build versus buy. 4. Performance and functionality. The performance gap is closing. Open source often offers more flexibility, like access to log probabilities.
What's the practical advice here?
The book suggests designing applications with a standard internal API. That way, you can swap models open, proprietary, different versions more easily as needed without rewriting everything. Gives you flexibility.
Public benchmarks seem like an easy way to compare, but they have big limitations.
They're useful for initial filtering, but definitely not the whole story for your specific application. First, limited coverage. Most leaderboards only use a few benchmarks due to cost and don't reflect your unique needs. Second, aggregation issues. Averaging scores treats all tasks equally. 80% on fact-checking might be weighted the same as 80% on simple math, even if one is way more critical for you.
We saw models like GPT-4 perceived as getting worse over time. It highlights evaluation challenges and that the best model overall might not be the best model for your application. You need internal application-specific testing.
And a major pitfall is data contamination. What is that exactly?
It's training on the test set, basically. The model sees the evaluation data during training, memorizes answers, and gets artificially high scores without true generalization. It can happen indirectly, shared data sources, or intentionally, fine-tuning on benchmarks before release. You detect it with heuristics like checking for text overlap or unusually low perplexity on evil data.
So, if public benchmarks are flawed, how do we build a robust internal evaluation pipeline? Chapter 4 lays out steps.
Yes, this is fundamental.
Evaluate all components. Complex apps have multiple parts. Evaluate end-to-end and each intermediate step. Like a resume extractor, evaluate PDF text extraction and employer extraction separately. Distinguish turn-based evil, each conversational turn, from task-based evil. Did the whole task succeed?
Step 2. Define evaluation criteria. This sounds like the hardest part. Deciding what good means.
Often is. Chapter 4 says, often the hardest part isn't determining whether an output is good, but rather what good means. Correctness isn't enough. Is it helpful, safe, relevant? You need detailed rubrics with examples for consistent scoring. And crucially, tie these metrics to business outcomes. Define how much automation 80%, 90% factual consistency enables. Establish a usefulness threshold.
Step 3. Annotate evaluation data. Getting the actual data to test against those criteria.
Right. Curate annotated examples for your components and criteria, ideally using real production data. Annotations can be human or AI-powered. Clear scoring rubrics are vital for consistency. LinkedIn found creating clear guidelines was a major hurdle. It's critical for reflecting real-world performance.
Step 4. Slice and dice data. Why break down the evaluation by segments?
To identify biases, for example, poor performance for certain user groups, or specific weaknesses, example, problems with long inputs. It avoids Simpson's paradox, where aggregate results look good but hide poor performance on subsets. It gives granular insights for targeted improvements.
And step 5. Evaluate the pipeline reliability, basically evaluating the evaluation itself.
Exactly. Are your signals right? Do better metrics mean better business outcomes? Is the pipeline reliable, repeatable? What's its cost latency? Its meta-evaluation to ensure your measurement system is trustworthy? And Chapter 4's advice. If you care about something, put a test set on it. These curated data sets can also be reused for data synthesis later. Chapter 8.
Okay, let's move to Chapter 5. Prompt engineering, often called an ARC. What's the core idea?
Fundamentally, Chapter 5 says it's about crafting an instruction to get a model to do what you want. Human to AI communication, easy to start, hard to master. The book warns prompt engineering's ease of use can mislead people into thinking that there's not much to it. It takes creativity, experimentation, and understanding how models interpret things.
A key concept is in-context learning. Zero shot, one shot, few shot. What do these mean, practically?
It means teaching models via examples in the prompt without updating weights. Introduced by GPT-3, zero shot. No examples, just instruction. One shot, one example. Few shot, multiple examples.
Does this change with newer, more powerful models?
Yes. For models like GPT-4, few-shot learning shows diminishing returns. They understand instructions better with fewer examples. But for specific domains or complex tasks, examples still make a big difference. The number you can use is limited by context length and cost.
And context length has exploded, right? From 1K tokens to 2 million.
It's been a race. GPT-2 had 1K. Gemini 1.5 Pro claims 2M enough for a book or large code base. This allows much richer prompts with more context and examples.
Let's cover key prompt engineering strategies. First, clear and explicit instructions.
Foundational. Be specific. Reduce ambiguity. If scoring an essay, explain the exact system. Fractional scores. What if unsure? Give examples of good-bad scores per criterion. More detail means better, more consistent results.
Adopt a persona, like asking it to be a grandmother or an NSA agent.
Exactly. It strongly influences tone, style, content. Act as a loving grandmother, it gets nurturing responses. Act as an NSA agent, gets formal, analytical ones. It helps tailor communication style effectively.
Task decomposition, breaking complex tasks into smaller ones.
Much more effective than one giant prompt for a support chatbot. First, intent classification, then response generation. GoDaddy improved performance and cut costs by breaking down their huge prompt. Modular prompts are easier to manage and debug.
Giving the model time to think. Chain of thought, karti sagati, and self-critique, how do they help?
They improve accuracy and reduce hallucinations. Carrot explicitly asks the model to think step by step. This nudges it towards systematic problem solving, improving performance on complex tasks like math problems. Self-critique asks the model to evaluate its own response and revise it, like 10 plus 3 equals 30. Is this correct? No, it's 13. It adds self-correction.
And finally, treating prompts like code, formatting and externalizing prompts.
Best practice, store prompts in separate files like prompts.py for reuse, testing, readability. Easier collaboration with subject experts too. Also, strictly adhere to the model's chat template tiny errors matter, and put instructions usually at the start or end of the prompt for best effect.
With more use comes more abuse. Prompt attacks and defenses. What are the main threats?
3 main types. 1. Prompt extraction, trying to steal your system prompt, your secret sauce. 2. Jailbreaking prompt injection, subverting safety filters or tricking the model into harmful actions, like the grandma exploit for napalm instructions.
Wow.
3. Information extraction, getting the model to reveal sensitive training data or context, like Gmail autocomplete revealing emails or Stable Diffusion generating copyrighted logos.
How do we defend against these?
Multi-layered defense. Use safety benchmarks. Do security red teaming. Explicitly instruct the model what not to return. Consider repeating the system prompt. Use safety boundaries like sandboxed code execution. Require human approval for risky actions. Use anomaly detection for weird prompts. Implement robust input-output guardrails. Track violation rate, attack success, and false refusal rate. Blocking legit requests, it's a balance.
What about indirect prompt injection? That sounds sneaky.
It is. Attackers embed malicious payloads in public content. Web pages, code repos. An AI using tools like web search might retrieve this malicious content. For example, an attacker puts malware install code in a GitHub repo. Your AI coding assistant finds it via search and suggests importing the malicious function. You execute it unknowingly. It highlights the need for careful safeguards around external tool use.
Wow, okay. Let's move to part 3. Advanced AI Engineering Patterns, Chapter 6, 7, 8. Starting with Chapter 6, Context Construction with R and Agents. Models only know their training data. How do we give them real-time or private info?
This is where patterns like R and agents come in. They provide information beyond the training data. RAG retrieves info. Agents can actively use tools.
Let's start with RAG, Retrieval-Augmented Generation. What's its core purpose?
RAG enhances generation by retrieving relevant info from external sources, databases, chat history, the internet. Chapter 6 says it connects the model with information it wasn't trained on or might have forgotten. It builds context specific to the query, giving the model up-to-date or proprietary info, crucial for things like internal knowledge-based chatbots.
What are the main components of a RAG system?
2 main parts. A retriever that fetches info, and a generator, the foundation model, that produces the response using that info. They can be fine-tuned together, but often use off-the-shelf parts.
How does the retrieval actually work, indexing and querying?
Yes. Indexing processes and organizes your data for fast retrieval. Often involves splitting documents into smaller chunks, sentences, paragraphs, to fit the context window. Querying fetches the most relevant chunks for a user query. Post-processing then combines these chunks with the original prompt for the generator model.
What retrieval algorithms are used? Lexical versus semantic?
Several options.
Uses keyword matching, like Elasticsearch, BM25. Fast, works well out of the box. But misses semantic, meaning transformer architecture, might return electrical device info.
Computes relevance based on meaning. Converts data and query to embeddings, finds nearest neighbors in a vector database. Can outperform lexical, especially with fine-tuning, but struggles with specific names codes, and embedding generation adds cost latency.
Often best in production. Use a cheap lexical retriever for initial candidates, then a precise semantic search to refine them, balances speed and accuracy.
How can engineers improve retrieval relevance in practice?
Several tactics.
No one-size-fits-all. Smaller chunks, more diverse info, but risk losing context. Overlapping chunks can help.
Refine initial rankings based on recency or other signals.
Expand queries with context. For example, what's its population becomes what's population of Paris. Can use another AI model for this?
Add metadata, tags, keywords, or summaries to chunks for better retrieval.
Use image, video, audio too. CLIP compares image and text embeddings for image search. Tabular data RAG. Use SQL executors to pull structured data from databases, needing a text-to-SQL step.
Got it. Now, the agentic pattern. What makes an AI agentic? How does it go beyond RAG?
Chapter 6 says, while RAG is primarily used for context construction, the agentic pattern can do much more. Agents can actively use tools, web search, APIs, calculators to gather info, perform tasks, or initiate actions. They decide which tools to use when, giving them hands to interact with the world.
What kinds of tools can agents use? What capabilities does this unlock?
3 main categories. 1, knowledge augmentation tools. Access external info, text-image retrievers like RAG, SQL executors, web search, APIs for inventory, email, etc. Web search keeps models current. 2, capability extension tools. Address model limits. Calculators, models are bad at math. Unit converters, translation, code interpreters. 3, write action tools. Act in external systems. Send emails, place orders, initiate transfers. Enables autonomous workflows but requires strong security.
Complex tasks require planning and execution. How do agents manage this? Why separate planning from doing?
Separating them is vital for debugging and efficiency. Process. Generate plan, validate plan, execute plan. Plans can be validated by heuristics or other AIs.
Use prompts to tell the model available tools functions. Practical tip. Ask it to report parameter values used. Generating natural language plans first, then translating to function calls often worked well. Reflection and error correction boosts performance. Agent evaluates request, feasibility, plan sense, progress. Self-critique prompts or specialized scorers help. Frameworks like React, Reason plus Act, or Reflection enable self-correction.
Agents sound powerful but failure-prone. How do we evaluate them?
Failures can be in planning, invalid tools barums, or tool use, bad translation, access denied. Evaluation metrics include percentage of valid plans, attempts needed for a valid plan, valid tool calls. For tool failures, track steps needed to complete a task, measures efficiency and robustness.
Agents also need memory systems for context over time. What are the mechanisms?
Crucial for multi-turn conversations. 3 mechanisms. 1, internal knowledge from training, static unless model updates. 2, short-term memory, context. Previous messages in the context window. Fast, limited capacity doesn't persist across sessions. 3, external memory, long-term. Persistent storage, like vector DBs for RG. Slower, larger capacity persists across tasks.
What are the benefits of memory in applications?
Maintaining context and consistency. Remembering previous answers avoids contradictions. Maintaining structure for data like storing sales leads in an external spreadsheet.
How is memory managed, especially for long conversations?
Strategies include FIFO, first in, first out, simple, but can lose early context. Summarization compression of old messages. Retrieval, RAG, to fetch relevant past segments. Fine-tuning the model to handle long context better. Choice depends on application needs.
Okay, Chapter 7, fine-tuning. Adapting the model itself by changing its weights. How's this different from prompting?
Fine-tuning means continuing to train a previously trained model, says Chapter 7. It changes the model's weights, adapting its knowledge and behavior. Prompting just guides existing knowledge. Fine-tuning modifies the underlying capabilities. It's a form of transfer learning.
What are the main types of fine-tuning?
3 main ones. 1, supervised fine-tuning, SFT, training on instruction-response pairs to teach specific behaviors or formats. 2, preference fine-tuning, RLHF, using RL and human comparison data to align with preferences, make it helpful, harmless. 3, long context fine-tuning, modifying architecture, positional embeddings, to extend context length, like Code Llama going from 4K to 16K tokens.
This raises a key question. When to fine-tune versus not and versus RA?
A critical decision. Reasons for fine-tuning. Specific instructions formats, most common reason. More reliable than prompting for consistent style, tone, or structured output, like JSON. New tasks. Adapting to tasks not seen in pre-training. Performance. Can improve quality, latency, cost, especially self-hosting. Efficiency. Can reduce prompt costs by embedding knowledge behavior in the model. Reasons not to fine-tune initially. High upfront investment. Needs data, slow costly annotation, and ongoing maintenance. Prompting first. Often sufficient results with less overhead. Try it first. Domain models. Powerful general models like GPT-4 can often outperform specialized ones now, reducing the need unless privacy self-hosting is strict. Fine-tuning versus RAG. Depends on the failure type. Fine-tuning versus RAG. Information failure. Lacks external info. Use RAG. Fine-tuning versus RAG. Behavior failure. Doesn't follow instructions. Wrong format tone. Use fine-tuning.
What about the practical constraints? Memory requirements for fine-tuning. Huge for large models.
A major challenge. Training uses backpropagation, forward and backward pass, needing much more memory than inference, forward pass only. Memory depends on total parameters, trainable parameters, and numerical precision, bits per parameter.
How does gradient checkpointing help?
It reduces memory by recomputing activations during the backward pass instead of storing them all. Increases training time but lowers memory needs. Chapter 7 notes. Reducing the number of trainable parameters reduces memory requirements. Gradient checkpointing enables this trade-off.
And quantization. Using fewer bits per parameter, what's the trade-off?
It halves memory going from 32-bit to 16-bit, even more for 8 or 4 bits. Great for memory saving. Inference often uses low precision. Training is more sensitive, often uses mixed precision. The trade-off is potential loss of precision performance, but often acceptable.
Because full fine-tuning is so memory-heavy, parameter-efficient fine-tuning, PEFT, is popular, like LoRa.
Hugely popular. PEFT drastically reduces trainable parameters, making fine-tuning accessible on cheaper hardware and needing less data. Hundreds, thousands of examples versus potentially millions for full tuning.
How does LoRa, low-rank adaptation, achieve this?
It adds small low-rank matrices, A and B, alongside the large original weight matrices, OUA. Only these small A and B matrices are trained. The original W stays frozen. Drastically cuts trainable parameters of memory. Chapter 7 says it's often applied to attention weights. WQ, WK, WV. Whoa. Very efficient.
What about model merging? Combining models.
Yes, merging combines parameters of multiple models into one, often for better performance or simpler serving. Different from ensembling, which combines outputs but keeps models separate.
How does merging work? Task vectors.
For models fine-tuned on the same base, you can use task vectors, the difference delta between fine-tuned and base model. These capture the task essence and can often be linearly combined. Goliath 120B merged 2 Llama 270D models this way. Merging can also use layer stacking for MoE models or other techniques.
Any practical tips for starting a fine-tuning project?
Base model selection. Start powerful. If it fails, weaker ones likely will too. If it works, then explore weaker, cheaper options. Frameworks. Use them. They simplify things. Beta volume. PEFT needs hundreds, full tuning thousands plus. DECT. Test with small sets, 5100 first for signal. Hyperparameters. Learning rate. Epochs. Batch size experiment. They're key.
Okay, Chapter 8. Data-centric AI. The unsung hero. Why is data so critical?
As Chapter 8 says, while not all issues can be solved with data, data is often a key part of the solution. Good data improves capability, safety, context handling. Bad data introduces bias, hallucinations. Data-centric AI focuses on improving performance by improving data, contrasting with model-centric AI, improving the model itself. Real progress needs both, but data fixes can be high impact.
What's the importance of data curation?
Actively selecting and preparing data sets for your needs, not just using what's available. Crucial for domain-specific needs and low-resource languages. Llama 3's training data focus, math, reasoning, code, shows this curated mix matters. Quality and diversity often beat sheer quantity. Test with subsets, 25%, 50%, to check diminishing returns.
How do teams get high-quality data beyond public datasets?
Several ways.
Leverage user interactions. Proprietary, huge competitive advantage.
Hugging Face, Kaggle, etc. But Chapter 8 warns, always check a dataset's license and inspect and validate. Not all public data is good or usable commercially. Annotating your own data, often necessary but hard. Clear guidelines are vital. LinkedIn found this a major hurdle. Manual data inspection. Greg Brockman, quote, staring at data for just 15 minutes, highest value to prestige ratio, find issues, automated checks, miss.
What about data augmentation and synthesis for creating more data?
Augmentation creates new examples from existing ones. Slip images, replace words, bias mitigation, rephrase, translate, add noise, perturbation for robustness like ImageNet-CP. Synthesis generates artificial data, great for privacy, can be rule-based templates or AI-generated using models like UltraChat or Alpaca. Nematron 4 used 98% synthetic data.
But AI-generated data has risks, like data lineage.
Big risk, obscures lineage. If the generator model used copyrighted data, your model might inherit violations. Chapter 8. Without clear data lineage, it's hard to assess commercial viability or trust its performance. Verify synthetic data quality.
And model distillation, using a big teacher model to train a small student.
Exactly. Goal, smaller, faster model with similar performance. Distilbert, 40% smaller, 60% faster. Alpaca, tiny model, fine-tuned on outputs from huge TextDaVinci 003. But license warning. Many licenses prohibit using outputs to train other models. Big legal check needed.
Finally, data processing best practices.
Critical steps. Filter and test scripts first. Do exploratory data analysis, EDA, check distributions, outliers, deduplicate data, clean data, remove HTML, PII, toxic copyrighted content, filter low-quality data identified during verification, use active learning if budget constrained, ensure correct formatting for tokenizer chat template.
Okay, part 4, scaling and operating AI applications. Chapters 9 and 10. Starting with Chapter 9, Inference Optimization, making models usable in the real world. Why is this so critical?
Because real-world value comes down to cost and speed. How much does it cost to run? How fast does it respond? Inference optimization tackles this. It's interdisciplinary models, apps, systems, hardware. If using an API, the provider handles it. If self-hosting, you need to do it.
How does training versus inference differ for optimization?
Training builds the model, learns. Inference uses the model, applies knowledge. Unless you're training fine-tuning, your focus is optimizing inference, which has very different bottlenecks.
What are the main bottlenecks in inference?
Two main ones. One, compute bound, limited by calculation speed, FLOPS, like the LLM prefill phase, parallel input processing. Two, memory bandwidth bound, limited by data transfer speed from memory, like the LLM decode phase, sequential output, loading weights. Knowing which one dominates tells you where to optimize.
How do we measure inference performance? Key metrics.
Need precise measurement. 1. Latency. Query to response time breaks down into TTFT, time to first token, perceived responsiveness. TPOT, time per output token streaming speed. Total latency equals TTFT plus TPOT output tokens. Look at percentiles, not just averages. 2. Throughput, output tokens per second across all requests. Higher throughput usually means lower cost. 3. Utilization, resource efficiency. MFU, model FLOP's utilization, compares observed throughput to theoretical max. Higher MFU equals better efficiency, cost savings.
What about AI accelerators like GPUs, their role and trade-off?
They're specialized chips. NVIDIA GPUs dominate, designed for parallel processing, ideal for AI math, much faster than CPUs, but huge energy consumers. An H100 uses 7,000 kilowatt year, like a U.S. household. Pushes need for efficient hardware and green data centers.
The FOC model-level optimization techniques, making the model itself more efficient.
Yes, reducing size or speeding up compute.
Includes quantization, fewer bits, pruning, setting params to 0 for sparsity, less common, distillation, small student mimics large teacher.
Techniques like flash attention speed up the memory-intensive attention calculations.
For sequential generation, speculative decoding uses a fast draft model verified by the target model. Inference with reference copies, input tokens when suitable, speeds things up. KV cache optimization, techniques like page attention, BLLM, manage the growing KV cache memory more efficiently for longer contexts. Kernels and compilers. Low-level kernels, like CEDA, are hardware-optimized code. Compilers translate ML models into optimized code using these kernels, foundational for peak performance.
In optimizing the inference service level, managing multiple requests.
Focuses on resource management across requests.
Combine requests. Static, fixed size waits, dynamic waits for size or time. Continuous, returns responses as ready, adds new requests, best UX, most complex.
Distribute model across devices. Tensor parallelism, split within layers. Pipeline parallelism, split across layers. Data parallelism, replicate model. Each has latency throughput trade-offs.
Okay, Chapter 10. AI application architectures. From simple to sophisticated. What's the basic starting point? Step 0.
The simplest setup. Query goes direct to model, API or self-hosted. Response comes back. No bells, no whistles, as Chapter 10 says. Good for prototypes or simple cases.
What's the first major enhancement needed for practical apps? Step 1.
Step 1, context construction, giving the model external info. Feature engineering for foundation models. Add RAG systems, agent capabilities, document uploading, ensures model has a relevant, up-to-date context.
Then, as things get serious, Step 2. Adding guardrails for protection.
Critical for mitigating risk. Input guardrails, protect against malicious prompts leaking private info. Output guardrails, catch qualitative failures like bad formatting hallucinations or security failures like toxicity, PI, unauthorized actions. Can be from model providers, app developers, or off-the-shelf tools, Meta's Purple Llama, Nemo guardrails. It's a balance between safety and usability.
Step 3. Model routing and gateways. Why add these layers?
As apps handle diverse tasks, one model might not fit all. Model routing sends queries to the best model pipeline based on intent. Example, support bot routes based on query type. Routers need to be fast. A model gateway provides a unified interface to multiple models, self-hosted APIs, simplifies maintenance, update gateway, not all apps, offers access control, cost management, fallbacks, logging, etc., central control point.
Step 4. Optimizing with caching. How does this apply to AI?
Improves performance, reduces cost by reusing results for identical request components. Good for multi-step processes, COT, or slow actions, retrieval. Types: KV caching, prompt caching, implemented in memory or databases, but warning, careful implementation needed to avoid data leaks. EEAI caching user A's private info, returning it to user B. Semantic caching is complex.
And the most advanced, step 5. Complex logic and right actions, agentic patterns.
Where AI goes beyond Q&A to autonomous action. Multi-step reasoning, loops, decisions. Right actions, send email, place order, dramatically increase capability but also risk. Needs sufficient caution and appropriate safeguards, says Chapter 10. Highest level of autonomy and complexity.
With this complexity, monitoring and observability become essential. What's the difference? Why is observability key?
Monitoring detects when something's wrong, external outputs. Observability ensures you have enough internal state info to diagnose what went wrong without deploying new code. Chapter 10. Observability is about instrumenting your system so that when something goes wrong, it can help you figure out what goes wrong. Proactive instrumentation for effective debugging.
What are the key metrics for AI observability?
Beyond standard MTTD, MTTR, CFR, you need AI-specific ones. Format failures, quality metrics, consistency, conciseness often via AI judges. Safety metrics, toxicity, PII, guardrail triggers. User behavior signals are crucial. Early termination, corrections, complaints, regeneration frequency, plus latency and cost metrics. Breakdown by user release prompt, trace requests step by step, request tracing, monitor for drift, prompt, data, model behavior changes.
Managing these complex pipelines needs AI pipeline orchestration.
Yes. Manages flow between multiple models, DBs, tools, 2 steps. Component definition, define models, sources, tools, and chaining, define how they work together. Tools, LangChain, Lemma Index, Flowwise, etc. Book suggests starting with Outline to learn mechanics, then add abstraction. Look for support for complex flows, ease of use, performance.
Finally, user feedback. The most valuable asset. Why so important? It provides proprietary data, a huge competitive advantage. Everyone has the models, only you have your user interaction data. Feedback is explicit, thumbs up, down, comments, or implicit, inferred from behavior. Early exit, corrections, complaints, regenerations. This closes the loop for continuous improvement.
What practical insights come from user feedback?
Rich insights. User preferences, book the one-year galleries, art interest. Corrections, Bill is the suspect, points out error. Signals distrust. Are you sure? Needs more detail. User edits to generated code is strong signal of incorrectness. Sentiment, tracks frustration. Understanding how the bot fails helps make it better. For example, prompt for conciseness if users dislike verbosity. Leveraging implicit feedback is key.
That brings us to the end of our deep dive. We've journeyed through Chip Huon's AI engineering, unpacking foundation models, their training, self-supervision, SFT, RLHF. We explored evaluation, model selection, data contamination.
And the practical techniques like prompt engineering, RAG, agents, and fine-tuning. Then the operational side, inference optimization, architectures, monitoring, and that crucial user feedback loop.
Our aim was really to give you, the listener, a solid grasp of how these real-world AI applications get built, evaluated, and optimized. Whether you're a developer, a product manager, or just deeply curious, hopefully this arms you with foundational knowledge.
It's about navigating the complexity and unlocking the potential.
And as we close, here's a thought to ponder. If AI models learn increasingly from data generated by other AIs, what new ethical and practical questions arise when the truth they learn is itself synthetic, maybe obscuring its own origins and biases?
It's a deep question, hinting at the ongoing evolution and challenges. We really encourage you to use this overview as a springboard for your own exploration. There's always more to learn in AI engineering.
Absolutely. Thank you for joining us on the deep dive. Until next time, keep learning and keep building.